Hi, here's my report for the fourth lab assignment. In this lab, we will analyze the spring mass system in Tracker and compare it with the motion predicted by Python using Newton's second law of motion and the energy principle. The three types of energies that are considered in developing the model are the kinetic energy, the gravitational potential energy, and the spring potential energy of the system. Let us now analyze the motion of the system using Tracker. We have a total of 98 time steps and 5 complete oscillations of the object which we can use for this analysis. The final time step I obtained is 9.333 seconds. The initial position at time step t is equal to 0 is also noted. From the position data, I got the x component as minus 0.113 meters and the y component as minus 0.633 meters. The average time period for the first three oscillations is 1.651 seconds. From this data, I calculated the spring constant K and the relaxed length of the spring L0 as 5.82 Newton per meter and 0.0231 meters respectively. Next we move to the Python model. I modified the mass of the object, the initial position at time t is equal to 0, and the calculated values of the spring constant K and the relaxed length of the spring L0. For the iteration, the final time step is entered. As per the respective relations, the code for the net interactions and energies in the system are entered. Now that the physics is in place, we can run the module and observe the predicted motion. In the motion window, the black arrow represents the gravitational potential energy, the blue arrow indicates the spring potential energy, and the green arrow indicates the net force. The experimental motion of the mass that we obtain from Tracker is depicted by the red sphere. In the graph window, changes in the kinetic energy, spring potential energy, gravitational potential energy, and the total change of energy can be seen in blue, red, green, and yellow respectively. When we compare the model and experimental motion of the mass, we can observe a considerable difference. This difference arises because there are some more interactions within the system that cause certain energy changes that are not accounted for in the computational model. These changes can be in terms of spring potential energy and the kinetic energy of the mass. The energy graphs, however, satisfy the energy principle, as we can observe that the yellow line indicating the total energy change in the system is 0. The changes in the kinetic energy, spring and gravitational potential energies vary in a waveform having both positive and negative values. From the tracker analysis, we can get estimates of the time period of oscillation. For this, we select the initial and final point of an oscillation and note down the position component on whose basis we want to calculate the time period. This procedure can be followed for all the 5 oscillations, and the time period for each one should be noted down for x and y components individually. In some cases, the final position components of successive oscillations were different, so I used interpolation to calculate the exact time step for the required positions. I calculated the time period based on an individual component data by calculating the average of the time periods for all 5 oscillations. The time period for x and y position data is 1.66 seconds and 1.55 seconds respectively. We can observe this difference between the time periods because the overall range of positions for y component is lesser than that of the x component. The x component gives a better estimate of the time period since the object's motion is varying considerably in that direction. However, the y component's effect on the time period is not negligible. It just does not vary considerably to give an accurate estimate of the average time period of oscillation.